It's recording. Right, so only 29 submitted. So any questions? Anything that you don't understand? Thanks, Virgin. Oh my God, I will read. Mugaraj, improve on the writing bit, okay? Okay, so it was exercise 1.1. It was cuboid, exactly the same thing. Okay, exercise 1.2 was a cylinder. Okay, so usually there is question for this, especially in terms of projected area. Okay, so any questions? Let me open something, any others with hopefully better handwriting. Okay. So this has been typed out. Okay, no problem. So the cuboid one I think should be fine, but then when there is cylinder, you probably had an issue on the smallest aperture as well as the projected area. Okay, so there will be, this one is for regular cylinder, 1 mm and 0.1 mm. I think the disc shape one will have the unstable position. Okay, so one of these you will have an unstable position because it's one of the sides is very small. So let me see. Nicely done, Munir. Nice. Okay, so yeah, this is very nice. So I can keep this for my future classes as well. For that, I'll just plug in the PowerPoint. Okay, so this is nicely done. So I think the formulas is not a problem. Okay, so you've got the sieve 0.1 mm. Okay, and then the particles has two resting position, 0.1 by 1, and the area 2, which is very small. Okay, so this is the area dimension 2 is the one that will be unstable because it is very small. Okay, and then for this shape we also have unstable position because this the thickness of it is very small. Okay, so it's unstable position. One of the projected area is also unstable. Okay, other than that, yeah, okay, I think this is quite good. And I'll keep this for future students to have it, to save it, to refer to. Okay, that's good. Okay, any questions? No questions? You are able to do it? So please submit it by tonight, yeah? Please submit it by tonight. I can even share what Munir's work as your sample example as well, in case you need reference, the other half of you. Okay, please remember to sign in attendance. Okay, so for today, it will be a very short class, so I am going to make some, since there is no question, so I will do a little bit of lecture as an introduction for for our Wednesday class. Slides. Slides are here. It's in. Let me just have a look at the documents. Okay, good. So there's 48 signed in. So in class, there's about 50 something of you. So please remember to sign in. So those who don't sign in, I'll immediately put in absent for you. So many clicking. I need to go to Teams and Files. And it's this one. Okay, so this is what we did last week. Okay, so today I want to discuss a little bit on particle size distribution and bulk sizing. Okay, so we have seen we know particles are very small, and so we don't buy particles one by one. Okay, we don't buy by grains. Like you don't buy one particle of sugar or one particle of rice grain. We don't do that. Okay, so we buy it in bulk. So this bulk sizing of particles also needs to be standardized. So different particles can be represented in different representation. Like you can either use surface, you can either use volume, you can either use numbers, you can either use mass. Okay, so these are the main four that we have now. So it depends on the type of the particle. We do bulk sizing of the particles. Okay. So I'm sure you can recall this from our statistics class. Okay. So we can have a symmetric and non-symmetric distribution of the product that we have. Okay. So we can have a non-symmetric with a mode, median, and mean at a different point. We can also have symmetric distribution where we apply Gaussian distribution to get a perfect dumbbell shape wherein our mode, median, and mean comes to the same point. Okay, so these are the options that we have. So in normal distribution, when we normalize our values, so we get the mean right in the middle, and then we can explain our product in standard deviations. One standard deviation, okay, and then two standard deviations. So in one standard deviation, you have 68% of the product lying in one standard deviation, and then 95% of the product in the two standard deviation. And if you go for 3 standard deviation, you get 99.9 products in that sampling. Okay, and so these numbers are fixed. Okay, so if you're talking about one standard distribution, so one standard deviation, you're talking about 68% of the sample. If you're talking about 95% of the sample, then it's 2 standard distribution, and so on. Okay. So we can also use excess value. Okay, so we can use D10. So D10 means 10% below this size, a particular size, this last 10%, okay, this last 10%. Or we can use D90, meaning 90% of the product, okay, 90% of that. So this part is 10%, so this is 90% of the product. Or we can also use 50% of the product. So we can also explain it as D50. Okay, these are ways we can actually explain what is our product size in general. Okay, because if let's say I buy a rice grain, so if you buy rice, right, in the packets, you still see they declare that there is 5% of broken rice, because during the handling it's broken. It's not added, it breaks during the handling. So that's why they say there will be plus minus 5% of broken buys. Okay, so we have to give an estimate of what to expect in every packet or every bulk product that I'm buying. What am I expecting from it? Especially now when you're doing a lot of internet business, online businesses and all. So there's a lot of communication taking place. You don't get to touch or feel the product. So you have to give a commonly understood product sizing so that the seller, the buyer, the customer are aware of what they are buying. They're informed of the product, the characteristics of the product. Okay, so this is where statistics comes in. So statistics is literally everywhere in our daily life. So whatever you learn in statistics may look like simple, foreign, unrelated, but it's not true. Okay, it's very much related in our life. The screen is. And so this one, so we can describe a population in either frequency distribution. Okay, you have learned what is frequency distribution. So for every particles, what are the number of what are the frequency that it is present? Okay, so that is frequency distribution. You can also have cumulative distribution. So cumulative is when you add on. So this is a frequency plot. This is a cumulative frequency distribution. This is a cumulative plot. So when you accumulate, it adds on. Two, frequency and cumulative are related. So when you integrate cumulative distribution, this is cumulative, the big F, is integral of the frequency distribution. So frequency distribution is the derivative of the cumulative distribution, and then it's vice versa. If I have the cumulative distribution, I can integrate. Okay, I integrate the frequency to get my cumulative distribution. So this is the relationship for the frequency and cumulative distribution. So later, in the later part of our particle size bulk sizing, we can use any cumulative or frequency distribution. So it can be, where is my pen? Okay. So I can, it can be numbers, or it can be mass, or it can be surface area, we've just learned, or surface to volume ratio, or just volume. It can be any. Okay, so let's move on. So comparison between distributions. So the distributions, the same particle, just like how you just did your exercise, the same particle, okay, you had a cuboid, but you are able to translate it into XS, XV, and then XSV. So we can also translate the same product into different distributions. Okay, there's more to it. So you could have also have X numbers. You could have also have X mass. These are the 5. Okay. Let's see the comparison. When to use what. So if I have very fine particles, this is like our green mung beans. Mung beans. Okay. So you don't buy mung beans in numbers. Okay. So let's say you have mung beans, and then these are bigger beans. What bean? There's a white bean that is as big as this, or it can also be an aquarium tank. The small rocks? Small rock is wrong. Okay, your aquarium fillers, and then but I think all these are beans actually, and then some black beans, okay, slightly bigger than the mung bean. Okay, let's assume all of these are beans of different size. So of different size but same number. So the same, you see, there's 13 beans of each size. Each of it we calculate 13 out. But if I put it in a cylinder, they give me different volumes. Okay, so I cannot tell you I'll be sending you 13 beans of this or 13 beans of it. If you have not seen it, you have never seen it, you won't be able to estimate how big your parcel is going to be. Let's say I'm buying 13 beans of 13 of each of this. How do I imagine how big my sample is going to be if I have never seen the size? How am I going to imagine? But if I put it into volume, and I say if one is going to be 1 ml, the other is going to be about 30 ml, 3 ml, and the other is going to be about 100 ml or maybe 20 ml. And then I get an idea. So my drinking bottle, okay, so if I'm receiving 100 ml, so I'm talking about, okay, roughly about this much, this size of it, this much of it. So you get an idea. So if I'm talking about something smaller, so I'm probably getting, this is about 5 ml, I think. So you get so you have an idea, you get something small, and this is like about 30 ml. So it gives you a comparison to evaluate what is the bulk size of the product that you're looking at. Okay. So if I were to look at equal volume, so this is how much I will get in number. The numbers will definitely differ for the equal volume. So these 13 beans will only be like this. So if I'm talking about equal volume, so I will get this many beans of each different size. So if I'm going to bottle it, or if I'm going to package it, so I put it in equal volume. I want 100 ml of it, 100 volume of it. So I have the same packet regardless of the number. Okay. So if the same particles, if I do volume distribution, okay, this is a volume distribution converted to area and number. Same product can give me different bulk sizing, bulk distribution. Okay, same product, I can have a different number sizing, I can have a different area sizing, and I can have a different volume sizing. Okay, this is reality of particles. Okay. So another comparison to show you mass and number distribution for man-made objects orbiting the Earth. There's so many objects that we send out, isn't it? We send to the space. So everything, we have satellites. I mean, each country has how many numbers of satellites, and then you have workstations. NASA has its own workstation. And then we also have some trial samples that goes out and then goes missing. We don't know where it is. Okay, so this kind of things which has been detected and so they are man-made objects. So if you go by size in number, so the very, very fine ones are bigger in number. Okay, very fine ones. And then followed by the 10 cms and then the 1000. So if I go by number, the percentage is the finer particles constitute of 99.3%. But if I go by mass, the 7000 contributes to 99.96 mass. That is taken up by the bigger particle sizes. Okay, so this is the difference. So both these are correct, both these can be used, but where and when we use it is important. So that's when we decide whether you want it to be mass, you want it to be number, you want it to be volume, surface area, or surface to volume ratio. Okay. So for a given population of particles, the distribution by mass or number and surface can differ dramatically. All are smooth continuous curves, but size measurement methods often divide the size spectrum into size ranges, and size distribution becomes a histogram. So you get different output for different products. So like I told you, so if you go by number, so this is the frequency of a particular bulk, okay? So where we measure the particle size. So if I go by Fn, N stands for number, then I get this number. So it is actually containing smaller particle size. But if I go by surface area, then I get something lower. So S stands for surface. So this is frequency of surface area. If I go for volume, so this is frequency of volume. So it gets smaller. So as it is, it's small numbers. So the volume and the surface area will be bigger than the volume. I mean, this is just an example to show you a same particle for different distribution can give you a different frequency plot. Okay. Right. I'm going to stop here. I'm going to stop here. So for next week, I will go in detail on how. Okay, I think it's the same ones. Next week, I'll go in detail on this part. Okay, where I name it as particles characterization, how we represent the graph and measurements. So next week we will learn how we can change from frequency to cumulative to distribution. We'll do some hands-on, and then we will learn how to convert between the particles. Okay, also there's also length I missed out. So you can have length, surface, volume, surface to volume, mass distribution, and one more is number distribution. But number is very rarely used because it's present here for Fm because of the formula, because this is density times by the number, but Fn is not a preferred, it's always used, the number is always used for other distribution, but you don't prefer to give in numbers because particles are like different sizes, and so it's not representative of a bulk sizing. Okay, so we will learn how to convert, and we will do some exercise on the conversion bit, including this is what was on the other slide, so including this worked example. So we will work through it in the Wednesday class. Right, so I'm done for this 1 hour class. So usually the first few classes will look like it's very short, and we have nothing much to discuss. But as we go on, usually students will have questions for their assignment. There are things that need to be explained. But if it goes on too long without questions or anything, then I probably have to start giving you extra questions to do in class for this class. So please do ask me questions, and I'll try to address it. Okay, so that's all for today. So any questions from your side? There's no assignment today, so please complete what has been given to you last week. Submit it. So next, on Wednesday, I'll give you a new assignment for the conversion bit. Okay, so I'll just download attendance. So if you have no question, then we can actually adjourn the class. Thank you for making it.
Thank you.
Thank you, Doctor.
Okay, bye-bye.
Thank you, Doctor.
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 Thank you, Doctor. Thank you, Doctor.
All right, bye-bye.
Thank you, Doctor.